Hi, everybody. Thank you, Ollie, and thanks for Wired for having us here today to chat about our work. Artificial intelligence is often spoken of as this magic sparkle dust that can fix any problem that humanity has. And I hope I'm not getting up here today and doing the tech world equivalent of telling you Santa isn't real or the tooth fairy isn't real, but artificial intelligence is not magic sparkle dust. What it is a powerful tool for unlocking humanity's problem-solving capabilities. And our team at DeepMind has helped prove that one of the problems we can help solve is energy consumption, which, as many of us in this room know, is a key contributor to climate change. But before I get into exactly how we went about that, I would love to give you all some context on DeepMind and exactly how we're building what we're building and how we got into this space. So the first part of DeepMind's mission is to solve for intelligence. What does this mean? By this, I mean we develop general-purpose learning algorithms inspired by how the human brain works. You know, our brains are amazing organs because we come into this world with absolutely no knowledge of what to do, how to live in it, and yet we interact with our environments, take in sensory data, and our brains learn how to accomplish a variety of tasks and do them well. At DeepMind, we're looking to develop general-purpose learning algorithms that do essentially the same thing. The same system with the same parameters with absolutely no pre-programming should be able to learn to accomplish a variety of tasks well. The second part of our mission is to use that intelligence to tackle real-world problems, so to make the world a better place. So stated succinctly, we want to develop general-purpose learning algorithms to tackle the problems that you and I face every day. Our first breakthrough was in the Atari Testbed. We developed a single agent to play hundreds of Atari games. And this agent only took in raw pixels, so it understood data from its environment through sensory information. There was absolutely no pre-programming, so it didn't have prior knowledge of the system. And it was given a reward function that it knew it needed to maximize score. You can kind of think about this as a robot in an arcade, watching a game and controlling a joystick. When the agent first started playing the game, it's not very good. It's missing the ball a lot. It's clearly trying to figure out what it's exactly supposed to be doing here to maximize score. Then, after about 300 games, it starts getting better. What happens in more time at about game 500 is actually really interesting because not only has the agent gotten quite good at playing the game, but it develops a tunneling strategy. AI actually has the ability to demonstrate creativity. Now, for the skeptics in the room, you might be saying, okay, but that game is really easy. How about something a little more complicated? Well, next, we developed an algorithm that some of you may be familiar with called Alphago. And essentially, Alphago was a learning system that we developed to play the ancient board game Go. And while the rules of this game are really simple, Go itself is intractably complex. There are 10 to the 170th power possible board positions of this game. Every time one player plays a stone, there are 200 possible options that open up for the board, so a 200 branching factor. Now, this essentially means that there are more possible board states in Go than there are atoms in the universe, which I personally find absolutely mind-blowing. This is why Go, for a long time, has been the holy grail of AI research, because if we were able to, kind of break Go, we could prove that AI has the ability to navigate through a mass amount of complexity to kind of show us a simpler system. So we developed Alphago, and when it was ready, we challenged Lee Sedol, who is an absolute legend of the game and one of the Go champions of the past decade, to a 5-game match. Alphago actually won 4-1 in this 5-game set, but I think what's most interesting isn't necessarily the win, though that was great, but is the fact that Alphago was able to show us that we could learn new information in a game that humans had believed they'd mastered. In game 2, move 37, Alphago placed a stone on the board that was contradictory to everything we thought we knew about how to play the game. Lee Sedol, who had just been out on a smoke break, came back in, looked at the board, looked puzzled, and went directly back out again. And what he later said about the move when the real intelligence was shown by the win at the end of the game was this. I thought AlphaGo was based on a probability calculation and that it was merely a machine. But when I saw this move, I changed my mind. Surely AlphaGo is creative. The move was really creative and beautiful. So what we learned through the Atari Testbed and through Go is that not only can AI show us creativity, but it also has the capability to discover new knowledge. even when humans have been playing a game like Go for thousands of years. Now, there's lots of information about AlphaGo out there, so I won't go further into it. You guys can catch the documentary. It's available on most platforms, including Netflix and Prime Video, which Stephen just mentioned. But I will say that one of the important bits is that we've continued to develop this algorithm. And actually, the latest models, AlphaGo 0 and Alpha 0, have learned mastery even faster than Go. And a single agent is able to play 3 games, so not just Go, but also shogi and chess. So what's that to say? All of this research we then use to tackle real-world problems. And for everyone in this room, we would agree that climate change is one of our biggest. Christiana Figueres is one of the key contributors to the Paris Climate Change Agreement. And in June 2017, she said this: the world has 3 years left to stop dangerous climate change. Now, it's October 2018. It means we have about a year and a half left to level CO2 emissions, or even better, to start them decreasing. Now, our team has focused on energy consumption because, to Stephen's point in the last presentation, demand or supply meets demand. So because energy production is a primary contributor to greenhouse gases, we've decided to hone in on energy consumption, and specifically to industrial systems, because large industrial systems are the cause of 54% of global energy consumption. So if we think about the average industrial system. Actually, let's simplify the average large industrial system and say, assume a power plant has about 10 pieces of equipment. Now, many of the mechanical engineers in the room will know that it has many, many more than this. But for this example, let's assume 10. And each of those components, so pumps, chillers, et cetera, might have 10 different set points, things you can manipulate to control energy efficiency, maybe temperature or pressure. Now, that's already 10 to the 10, or 10 billion possible configurations of that plant. Now, that's just too much for a person to try to adjust. So what ends up happening is facility managers pick the most important, since what they deem the most important components to adjust and the set points on those components. And that amounts to, because the configurations are in the billions, that amounts to about 1% of the possible optimizations, leaving the other 99% untouched. And if this complexity wasn't difficult enough to try to manage, the system is also changing. New equipment is brought on, old equipment goes out for maintenance, things break. So while these facilities have traditionally been run by pre-programmed sets of rules, heuristics, they're changing systems. That's not okay. It would maybe be for a static system, but not for a changing one. You can think of self-driving cars. It's one of the examples that I've heard a couple of times today. And those cannot be programmed in an if-then capacity because there are simply too many scenarios they might run into, right? They need a self-learning system. And that's essentially similar for large industrial systems. So in 2016, we partnered with Google, and we decided to hone in on data centers because data centers consume 3% of global energy. And like playing Go or Atari, they have concrete actions and measurable rewards in their operation. What we did was we looked at over 2,500 data trends and a space of 20 actions. And we developed an AI system that essentially tried to reduce the energy required to cool Google data centers. Now, how did this work? We started with every 5 minutes, we took a snapshot of the data center cooling system. We took that data and we cleaned it and prepared it to be fed into the models. The models then selected actions by doing 2 things. 1, ensuring that all actions satisfied a robust set of safety controls. And 2, choosing actions that minimized future energy consumption. It then generated a set of recommendations on which set points to change and by how much, and gave those to a human operator who then went and manually implemented this in the system. Now, what we saw was pretty exciting because when our machine learning controls went on, there was a very clear dip in the amount of energy that the facility was consuming. And then when they went off, energy consumption went back up. So for those of you that are wondering how much this delta was, it was up to 40%, which we thought was a pretty fantastic number. But what's interesting is that the facility managers still had some feedback for us. They said, this amount of energy savings is fantastic, but when we were being run on pre-programmed sets of rules and heuristics, we didn't really have to be involved in the system. Can you kind of take us back out? We want to be back in a supervisory capacity. We said, okay, we took that feedback and said, what you're essentially saying is you want to have direct AI control of the data center cooling. Okay, we think we can do that. So phase one of autonomous control looks very similar to our recommendation system. We took snapshots of the data center cooling system through all of those data trends and the sensors. We cleaned the information, cleaned the data, got it fed into the models. The models, again, went through a robust set of safety constraints to select actions that would minimize future energy consumption. But at this point, instead of feeding them to the human operators to manually change those set points, we sent them directly back to the data center to run it through its own robust set of safety constraints before implementation. Now, if you notice, I've said safety more than a couple of times in the last couple of slides because it is our utmost, it is our very top priority in developing this system. So I'll run you through a couple of the things that we did. One of the things, we developed no less than 8 safety mechanisms in no particular order, being continuous monitoring to ensure that the AI did not violate any safety constraints, automatic failover to a neutral state in case it did, smooth transfer between these states just so there wasn't any sudden change to the system, 2-layer verification. This is when I mentioned that we ran our recommendations through our own safety constraints as well as those of the local system. Constant communication between the cloud-based AI and the local physical infrastructure of the data center. Uncertainty estimation, so we ensured that only the highest confidence actions were selected for our recommendations. Rules and heuristics as a fallback in case we needed to exit AI mode. And as always, human override available to exit AI mode at any time and also supersede any AI actions. Now, I know 8 different safety mechanisms might seem a bit redundant, but safety was just our absolute top priority. From our understanding, there is no other industrial facility this size that is being run through direct AI control. So the first thing we always have to consider is safety. And even though the models are being more conservative because of all of these constraints, what we're still seeing is a 30% reduction in energy consumption, and that number is growing. Because one of the best things about AI is that while rules and heuristics don't get better, AI does. You can see that the blue line, which indicates our training data, the more training data we have, as that blue line goes up and to the right, the more decrease we get in energy consumption. So this kind of green-gray line is the amount of energy consumption we saw at the data centers. So essentially, the more data we have, the more effective our models can be. And one of the most fun bits is getting feedback from the data center operators, the experts that we have been developing these systems for in the first place, commenting on the fact that they love seeing the new knowledge that AI has kind of learned how to manipulate the system to make it run more efficiently. So you might be wondering what's next. Well, right now our team is really, really excited that we've been able to deliver efficient, effective, consistent savings with our safety-first autonomous control system for the Google data centers. So we're really right now concentrating on rolling this out to more data centers. But imagine the possibility. I mentioned earlier that industrial systems, large industrial systems, consume 54% of global energy. And imagine the potential if we could apply this technology to industrial systems at large. We believe that there is that potential and that we could possibly affect climate change at an even grander scale. Thank you.
A really exciting glimpse of the future. I mean, for a lot of people, as you mentioned, there's a lot of discussion about AI, but the actual real world, to use it in a real world setting, in physical buildings, as you say, with people involved, it's a very different scale from what you were doing with the Atari Testbed and with Lisa Doll and the other work that you've done with Alphago. What have been the kind of learnings for you trying to apply this in a real world setting? As you said, it's huge security implications. There's a lot of, I imagine, complicated work that goes into that, and I'm interested in your journey as to using this in a real-world setting?
Yeah, applying this technology in the real world is always messy, as we're aware. The real world is messy. But I think the key learnings for us is the first being that including the data center operators, these experts that we're building these systems for in the first place, including them early and often will always set you up for success. Also ensuring that you have great data quality. Our models have to learn off of good data, and having that data and having the quality of system level data is really important. And then I would say the third thing would also be going back to the data center operators and these domain experts that have decades and decades of experience. they can really help us understand the safety constraints of any system. And for us, I mentioned safety lots of times because it's really important to us. And in order to build something that delivers on what your experts ask of you, you obviously want to make sure it's safe and effective. So you have to understand how to go about that.
Well, plenty of food for thought and discussion in our coffee break, which we're about to go into. Please give a massive round of applause and thank you to DeepMind for giving us that.